Hello and welcome to The Explainer. Today, we're diving into a pretty fascinating question. How does a robot actually see the world around it? Let's get into it. Alright, so here's our game plan. First, we'll cover the basics of how robots see. Then we'll dig into how pictures get turned into pure math, and how that math creates actual meaning. After that, we'll check out a totally different way of seeing, using lasers. And finally, we'll pull it all together to understand a robot's complete picture of the world. Okay, let's jump right in. We're going to start with the most common tool robots use to see, the camera. So, you know how a lot of robots have things that look like eyes? Ever wondered what's actually going on behind them? Well, for a huge number of robots, the answer is something we all use every single day, the digital camera. Yep, it's often the most direct way for a machine to just take a snapshot of its environment. And seriously, they are everywhere. I mean, think about the complex systems in self-driving cars, or those incredibly fast robotic arms on an assembly line, and even some of the newer home gadgets. Cameras are basically the go-to eyes for countless machines, letting them identify what's going on around them. So, a robot has a picture. Now what? How does that visual image get translated into a language a computer can actually process? This is where it gets really cool. It's basically a journey from art to pure arithmetic. And here's the key thing to get. A computer doesn't see a beautiful sunset or a cute dog. It sees data. That's it. So its very first job is to change that image into a format it can understand, which is a big old grid of numbers. The whole process kicks off by breaking the image down into the smallest possible pieces. You've heard of them. They're called pixels. We're talking thousands, sometimes millions of tiny little dots, and each one holds a tiny bit of information about its own color. And how do you organize millions of these tiny dots? You stick them in something called a matrix. Honestly, the best way to think of it is as a giant spreadsheet. Each cell in the spreadsheet is a single pixel, and the number inside that cell tells the computer its color. A picture literally becomes a table of numbers. Just think about a normal high-def screen. When you hear that it's 1920 by 1080, what you're really hearing are the dimensions of that matrix. That's 1920 columns and 1080 rows of pixels. It adds up to over 2 million tiny little data points that build the image we see. Okay, so the robot has this giant grid of numbers, but that's all it is, just data. The real question is, how does it turn all that raw data into actual understanding? This is the absolute magic of computer vision. It's this whole field dedicated to teaching computers how to interpret the visual world. By running some clever math operations on that big matrix of numbers, a robot can start to identify things, like, hey, that's a person, or that's a bike. One of the most powerful tools for this is a mathematical operation called a convolution. Now, don't worry about the fancy name. Just think of it like sliding a tiny little magnifying glass, they call it a kernel, across the entire grid of numbers. As it moves, this kernel looks at a small patch of pixels at a time, searching for important patterns and features. So how does it find something as simple as an edge? Well, it's surprisingly easy. An edge is just a place in that big grid where the numbers suddenly change. A high number right next to a low number, say a bright pixel next to a dark one, signals a boundary. A convolution is perfect for spotting exactly those kinds of sudden shifts. So this is the whole pipeline right here. First, capture the image. Second, turn it into that big matrix of numbers. Third, run convolutions on it to find all the important features like edges and textures. And finally, you feed all that process data into an AI model that's been trained to look at those features and tell you exactly what it's seeing. But cameras aren't the only way for a robot to see. In fact, let's move on to a totally different method that solves one of their single biggest problems. So here's the catch with cameras. They're passive. That means they have to rely on whatever light is already in the environment to work. And that is a huge problem if you need a robot to work at night or in a warehouse that's poorly lit. And that's where Lidar comes in. Lidar is an active sensor. It doesn't wait for light, it makes its own. It shoots out quick pulses of laser light and then measures exactly how long they take to bounce back. By doing this, it can calculate distance with incredible accuracy. So, just like a camera image becomes a matrix of colors, Lidar data becomes a matrix of distances. This is called a point cloud. It's basically a detailed 3D map where every single point tells the robot exactly how far away something is. Now, a Lidar's view of the world is very different from ours. It doesn't see any colors or textures at all. It sees the world purely in terms of shape and distance. But for something like a self-driving car, this is perfect. It's way less interested in the color of the car ahead and way more interested in exactly how far away it is so it can avoid a collision. So we have these two really powerful but really different ways of seeing. Let's put them side by side to really understand how they create a complete worldview for a robot. This really is the perfect summary. The camera is passive and it gives you all this rich color data that's ideal for identifying what an object is. You know, a stop sign, a person, a traffic light. Lidar is active, and it provides super precise distance data that's perfect for navigation and figuring out exactly where things are. It's the what versus the where. But the real power, the real genius, comes from using them together. By fusing the what from the camera with the where from the Lidar, a robot can build an incredibly detailed and robust model of its environment, and that lets it navigate safely and interact intelligently. And that brings us to our final thought. Now that you know the difference between these two types of robotic eyes, the camera for identifying things, and that often spinning Lidar for navigating, where will you spot them out in your own world? Look closely at delivery bots, modern cars, or even automated vacuums. You might be surprised at just how many robotic eyes are looking back at you.